This is a lecture on section 2.5, the atomic mass scale and average atomic mass. So one question that comes up, and we'll need to discuss this, is how much do atoms weigh? The answer, a very short answer, is not very much. In fact, one tiny speck of dust, which is probably the lowest mass that we could easily measure, has as many as 10 to the 16 atoms. That's a number given in your textbook by Burge. Now, let's look at a couple of pieces of information here. One carbon-12 atom weighs 1.993 times 10 to the negative 26 kilograms, very small mass. It's such a small mass that what we'll do is we'll create a new unit called the atomic mass unit and set it up so that the numbers in that atomic mass unit aren't so small. And here's the result of that. An atomic mass unit, 1 AMU, is equal to 1.661 times 10 to the negative 27 kilograms. Now, by agreement, the carbon-12 atom has a mass of exactly 12 AMU. Remember that notation, carbon-12 is a specific isotope of carbon. And we could write it like this, where 6 is the atomic number, and 12 is the mass number. This is a bit of review from the earlier sections. And if we look up in the periodic table, we'll find that the atomic number of carbon is 6. The mass number, since that's 12, we would say that the number of protons in this isotope, one atom, would be the atomic number 6. That's the number of protons. And then the mass number is 12, so the number of neutrons would be the mass number minus the atomic number. Let's make this equals 12 minus 6, so that equals 6. So this specific isotope of carbon has 6 protons and 6 neutrons, so it's perfectly balanced in terms of the numbers. Now, what would the mass of one atom of carbon-12 be in kilograms if we know that the mass is 12 AMU? We could use this conversion factor here. Okay, so we know the mass is 12 AMU. And we want to convert it to kilograms, so kilograms is here, so we're going to put this in the numerator. So we're going to multiply it by the ratio, 1.661 times 10 to the negative 27 kilograms. And we're going to divide that by 1 AMU. And here we go. So I'm going to calculate this. 12 times 1.661 times 10 to the minus 27 divided by 1, and you get 1.993 times 10 to the negative 26 kilograms. Now note, my calculator showed 1.9932, but I rounded it to 1.993. Now why did I do that? We're multiplying. This has 1, 2, 3, 4 sig figs. This is an exact number. Our number of protons and neutrons is known. It's not 12.1 or 12.2. It's exactly 12 is the mass, and this is the definition. 1 AMU exactly is this mass. So we have 4 sig figs here in this number, so I'm going to use 4 here. So 1.993 times 10 to the negative 26 kilograms. That's a very small mass for the carbon-12 atom. So how do we know, or how do we measure these masses? It turns out that each element has multiple isotopes in nature, and we can determine this one way is through a technique called mass spectrometry. And it's a very powerful technique that's been around for a while now, developed during the 1940s, 30s, and 40s. We have much more sophisticated devices today. This is a relatively old, simple type of design that's still used today. Let me show you. It's relatively easy to explain how the method works using this diagram. So the idea is, imagine you have something and you want to know what its atomic mass is, how much it weighs. We're talking about atoms now. What you would do is you'd put in a sample, and an important aspect of this is the sample has to be converted into the gas phase. So if you can use a heater to boil it, essentially vaporize it into a gas, then this device would work. If it were something very, very difficult to boil, so even at high temperature you couldn't vaporize it, then we would have to use some other method of analysis. We still could use mass spectrometry, but we wouldn't be able to use this heater here. Now, let's assume that the material we're looking at can be vaporized by this heater, and so it's a cloud of gas molecules or atoms, and we now put in an electron beam. Remember, the electron is the subatomic particle. It's negatively charged, doesn't have much mass. It can be accelerated by using electric fields or voltages and magnetic fields. So assume these electrons are just flying through and they start striking this cloud of gaseous atoms. What will happen is those electrons will knock off other electrons. So each electron might knock off one electron from the atom. Now that atom has a positive charge, so you start getting positively charged atoms, which we call ions. We'll talk more about them in the next section. Those ions then can be accelerated by applying electric potentials, voltages essentially. And so these disks have voltages applied to them, but they also have little slits here. So those positive ions will be accelerated through those disks in this particular direction. And again, it's electric potentials on those disks that are causing the positive atoms, positively charged atoms, to accelerate through. And then you put a magnet here. And what happens is the magnet will interact with these positively charged ions. So imagine them flying through space here. And they interact with this magnetic field. What happens is the particles that are lighter, the atoms that are lightest, will be deflected by the magnetic field the most. So they'll bend at a large angle here. The ones that are heavier are harder to deflect. So they'll get deflected too, but less so. And so notice in this diagram there's 1, 2, 3, 4, 5 streams. And this one right here, these ones would be the heaviest. And the ones that get deflected the most would be the lightest here. And then you'd have some sort of detector that's sensitive to the collision of these ions with its surface. Okay? So that's one method. There's other types of mass spectrometry, but they're all sort of based on the same idea, which is you put in a sample, somehow ionize it, and then deflect it with electric and magnetic fields, and then detect them. This is called a sector device. So here's one result. Tin, I found this on the internet, it's very interesting, mass spectrometry of tin. Tin has a lot of isotopes. So 112, 114, 116, 117, 18, 19, 20, a lot of different isotopes that are found in nature. And so these are the mass numbers here. So this would be tin 112, tin 124. Okay, just so that we can remind ourselves from the earlier discussion. Tin 124, tin 112, that's one way to write them. Of course, we could also write them, put the mass number at the top. And since it's element number 50, we get that number from the periodic table. It would be tin 5112, tin 5124. Now, these numbers are percentages here. These are percent abundances. And so what this says is that when tin, a sample of tin atoms, was run through a mass spectrometer, 0.97%, almost 1% of it came out as tin 112. And look at all these numbers. They should add up pretty much to 100%. And this is what the data might look like. It's a printout of what would show up on a computer screen. And it shows that at these atomic masses, 116, 117, 118, 119, so forth and so on, these are where the masses showed up. And so notice there's nothing at 119, so that means that tin actually 119 is 8.6%, so I'm not sure where that number showed up. There's 118, there's 120. 119 is missing from there for some reason. So maybe this is a sample that for various reasons didn't have 119. But these are the atomic masses of those isotopes shown here on the graph. Now here's a simpler element, copper. Copper really only has two isotopes that are generally found in nature, copper 63 and copper 65. And so this is a readout. Notice we get a big broad peak around 63, and we get a big broad peak around 65. And notice the area for the 63 is larger than the area under the curve for 65. That means there's more of the copper 63 in the sample and less of the copper in the 65 sample. So the area tells us how much, that gives us the percentage. So what you would do is you would add up the area of this and this together. That would give you a total. And then if you took the area of this one over the total, you'd get 69% after you multiply by 100. So the area of the first peak plus the area of the second peak is the total area. And the percent of copper 63, we'll call this A1, area 1, A2, area 2. Copper 63 would be the first area, A1, divided by area total, times 100%. And you could do the same thing with this one. This would be copper 65, so area 2 over the total area times 100%. And so that's what they did here. They got 69% for this one and 31. In fact, you could, even doing this in a very primitive way, what you could do is you could actually print this out on a piece of paper, cut out very carefully this curve, this peak, do the same thing for this one, and weigh them to get their areas. And then you could calculate using this ratio here. Just add up the areas of, or the weights of those curves. So that's mass spectrometry. It can also be used to measure compounds. So imagine we have a very heavy compound with lots of carbon, hydrogen, oxygen, nitrogen atoms, and it weighs around 712 atomic mass units. Just for reference, hydrogen is approximately 1 AMU. Oxygen is approximately 16 AMU. So every time, if you were to take a molecule and add an oxygen to it, it would get heavier by 16 AMU. If you were to take a molecule and add a hydrogen to it, it would get heavier by 1 AMU. So take a look. This is one type of molecule, but notice that it has 4 different peaks. One very high, tall peak, one that's shorter but still pretty tall, one that's shorter still, and one that's very, very tiny. Notice the masses, the overall masses differ by almost exactly 1 AMU, right? So 712, 713, 714, 715, they're all about 0.4. That's because what's happening is this molecule has fewer hydrogens by 1 than this one. So this one has an extra hydrogen atom. This one weighs 2 AMU more than that one, so it's got 2 extra hydrogen atoms. And this one's 715 versus 712. It's got an extra 3 hydrogen atoms in the molecule. So you can measure now chemical differences, structural differences between molecules based on measuring the atomic masses. Okay. So now let's take a look at a very common type of calculation. This is probably the primary type of calculation you'll need to be able to do in this section, and that is to calculate the average atomic mass of an element. So I picked lead here because lead has 4 isotopes listed, and so I thought we could go through this particular problem to show you how to go at it. We're going to consider these lead isotopes. Remember their notation, you put the mass number at the top on the left side, so lead 204, 204 Pb. The symbol for lead is Pb. We can look that up in a periodic table if you don't remember it. Now, what we're going to do is we're going to calculate the average, and this is called a weighted average. Okay. And weighted doesn't mean that we're weighing it specifically. What it means is we may not have the same amount of each particular particle that we're interested in. So notice lead 204, only 1.4% of the total lead in the sample is lead 204. But lead 208, for example, is 52.4%. So they're not equal amounts. If we wanted to just take the simple average of these 4 isotopes, that assumption would be that each of these are 25%. So 1 out of 4 is each isotope. Then we could just add these up and divide by 4. That's called a simple average. But that's not useful for us because in nature, isotopes don't generally occur in equal amounts. They occur in quite varied amounts. So what we have to do is a weighted average. So the weighted average is similar to a simple average. The total, notice this is percent, the total is 100%. So here's how we do the calculated weighted average. You take the percent of the first isotope. So I'm going to call this isotope A, isotope B, isotope C, and isotope D. Okay, just for notation. So you take the percent of the first isotope, isotope A, divide that by 100. This converts it to a decimal number. And then you multiply that by the atomic mass of that specific isotope. In this case, it's A. Then you add that to the second isotope, isotope B. So this would be percent B over 100 times the atomic mass of isotope B. Okay? And you keep on going until you run out of isotopes. So the third isotope is isotope C, so percent C over 100 times the atomic mass of C. And there's one more here, so let's add that down here, plus the percent of isotope D over 100 times the atomic mass of isotope D. Okay. Now what I'm going to do, this is the weighted average. I'm now going to go ahead and substitute in the numbers that we have here. So let's go ahead and run through it. So for lead, isotope A is lead 204, and it has a relative abundance of 1.4%. So 1.4 over 100 times its atomic mass, 203.973,020. Now I'm going to go ahead and put the A units in there, AMU. Now we'll do the second isotope. Second isotope is lead 206. Lead 206 is 24.1%. So 24.1 over 100 times its atomic mass, 205.9744440 AMU. Okay, we're going to add that to the third one. The third one is isotope C, or lead 207, 22.1 over 100 times 206.975872 AMU. And then we got one more, which is lead 208, 52.4 over 100 times 207.976627 AMU. Okay. And what I would recommend doing when you do these problems is just go ahead and calculate this out as one term, calculate this out as a second, this one is a third, and this one is a fourth. So I've done that already, and what I came up with is 2.85562 AMU plus 49.63984 AMU plus 45.74 166 AMU plus 108.97975 AMU. Okay, so there's our four numbers. Now we can add those together and we get 207.21 687 AMU. And now let's consider significant figures. So notice we have 2 sig figs here, but we have a lot there. But remember, when you're doing multiplication, so I'm going to come back over here, 2 sig figs, a lot of sig figs, multiplication. This one really only has 2 sig figs. Remember, with multiplication division, you pick the number that has the fewest sig figs. So that first answer there, 2.85562, only has 2 sig figs. So I'm going to put a little line there. That's our second sig fig. 1, 2. You go from left to right. Second one, 24.1, 3 sig figs. A lot of sig figs in the atomic mass, but only 3 here. It's multiplication, so that limits it. So 3. So 1, 2, 3. Third calculation, 1, 2, 3 sig figs there. A lot of sig figs there, so we'll limit it by 3. 1, 2, 3. Again, I'm putting a line over the third sig fig because this calculation should only have 3 sig figs. And our last one, 1, 2, 3. Again, it's the percentage that's limiting it. But notice the third sig fig here is this one in the ones column. So now when we add these four numbers together, I'm going to go ahead and add them in the calculator and go all the way out here 5 digits past the decimal point, but now I'm going to round it according to the rules of addition. The rules of addition is you count to the right of the decimal point. So if this one only goes 1 digit past the decimal point, then that one should only be 2 sig figs. This one goes 1 digit past the decimal point, so that'd be 3. This one goes 1 digit past the decimal point, so that'd be 3. This one goes, see, this is in the ones column. So this doesn't even go 1 past the decimal point. It's to the left of the decimal point. So this would have 3 sig figs also. So now when you add them, you pick the one that goes the farthest to the left. And that would be this one. It's in the ones column. See, this is in the tenths, and tens column, but this is only in the ones column. So our answer can only be in the ones column. So we would round it to the ones column. This is less than 5, so we just leave it at 207 atomic mass units. So notice the actual rounding is done at the end, not in the intermediate steps. If you round each time, round this to 2 sig figs, round this to 3, round this to 3, round this to 3, and then add them up, you will get a different answer, or you could possibly get a different answer. So round it at the end after you run through the calculation. And that ends our discussion of atomic masses.